Alright, so you made it to my section 1.1 video for Math 142, which I'll get to the material really quick here. Before you get started, it couldn't hurt to have the answers that are for the odd problems in this section kind of at your fingertips. And those are on my web page. And in case you haven't been to my web page yet, I'll show you how to get there, show you at least where the answers are at. There's lots of stuff on my web page, and in class I will show you what's there and what you're going to need for this class. But real quickly, I'm going to flip over to the computer and show you, how to quickly get to my web page and again what's on there. So real quickly, I've got to shut this screen off and flick over to my computer. So that's my web page, my YouTube page. I'm assuming you got to my YouTube page because you're watching the video. There's a link on my YouTube page to my web page, and it's almost unreadable at this point probably. You probably won't be able to see too much of what I have displayed here, but the thing that you're going to need to do is you're going to need to follow the link to this course, so that I'm pointing to Math 142 College Math, and once you get to that, you'll get all the material that we need for our class is going to be here. And for this morning, or whenever you're watching this, if you click on the link that says Problems and Answers, and then you click on the link again, you probably can't read this because it's showing up too small on your screen, but if you click on the link that says Section 1.1, everything I'm about to do in this lecture is going to be contained here. So I've written kind of my lecture notes along with problems that go along with this section, and it's all contained under this link. And if you scroll down to the very end of this section, there's something that says answers. Every odd problem in this section has answers, and this is what you should have this at your fingertips as we get into the lecture so that you can kind of check yourself. The idea is when you're watching my videos, you should be doing homework while you're watching the video. So by the time you're done watching a video for a section, you've done everything you need to other than study for the test, meaning that you've taken all the notes that you need to take, and you've done all the homework questions. Generally, the homework is to do every odd problem in the section. So again, if you aren't on my aren't on my YouTube page, you can just go to Canvas, and I'll have a link for my web page on Canvas. And once you get to my web page, you can bookmark it, so you can just have it there all the time. All right, so that's all I want, is just to make sure you have access right now to the answers to this section, because as we're going through this section, you should be checking your answers. You should be doing homework along with me, and you should be checking your answers. So those I won't have displayed, but you should have either be able to flick to the screen on your computer that has the answers or print these out. I don't expect you to print out all the material that's for every section, because that would be kind of a waste of ink, and I know ink's not cheap. So what I'm going to essentially do is go through the stuff that I have typed up in under the section 1.1 problems heading, and try to explain everything that you need to do the problems in this section. In chapter 1, there are a lot of definitions and theories that you may have never seen before. So there's a lot of work that I'll do before I actually get into the problems. When we get to the tests, the only thing you're ever going to be responsible for is to be able to do problems that are similar to the homework problems. So you could theoretically, if you're feeling pinched for time, you can fast forward the video until when I start doing problems, although it might like the problems not that easy to follow. But if you fast forwarded to here, I might talk well enough or explain well enough the problems that if you miss these, first 4 pages of explanation, 4 pages in big print, probably a page in small print of explanation. But so if you wanted to, you can roll the dice and fast forward to there and try to do those problems with me. If not, it would be better, especially because it's the first lecture, just to sit through and listen to me say what I have to say. I'm not going to essentially say anything that isn't already typed up, so you don't really have to take notes. Everything that I say will be on my webpage, but if you want to take notes, you can. So this first section is called an introduction to sets, and then depending on when you went to grade school, you're either a little bit familiar with sets or completely unfamiliar with sets. I went to grade school in the 70s, and we studied sets every year between 1st and 8th grade, so I was pretty familiar with them. So a set is just a collection of objects, and that's really a pretty horrid definition. It's not very descriptive as to what a set is. This is because there's a lot of latitude in terms of what we call a set. And we'll get to that here in a second, but I should say a little bit more. So a set is a collection of objects. Each object in a set we can call an element or a member. And I'll use the word elements and member kind of interchangeably, and I'll use them like you know what they are. An element is just something that's an object inside of a set, an object that's contained in a set. And when we name sets, we usually name them with capital letter names. So sets, collection of objects. The objects inside the sets are called elements or members, and we usually give names to sets with capital letters. So here's my first example, just to give you an idea of something that would fit the definition of a set. So let A be the set, so I'm calling it a set, so I'm kind of telling you it's a set in the explanation, of integers between 2 and 5 inclusive. List the elements of set A and place the elements in set braces. This is probably a lot to ask at this point because there's a bunch of words in here that you might not be familiar with, and the words that are probably that I bolded are the words that I suspected that you might not understand at all. Also, I probably should have bolded set braces because you might not understand that either. So I want to list the objects or the elements in set A, and in order to do that I have to understand the word integers, inclusive, and set braces. On the next page I probably write up what those words mean, but I'm going to just write it here on this page so I don't have to flip away from this. So the first word that I had bolded was integers, and integers are essentially positive and negative numbers that don't have fractions and decimals. So like -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Those are all considered integers. It's impossible for me to write all the integers because there's infinitely many of them. So on either side of my list, I'm going to put a ... meaning that pattern continues, so going up by 1 to the right, and a backwards ... meaning that pattern continues to the left. So those are what integers are. Notice I put this little squiggly bracket. This is called a set brace. And if you're listing the objects in a set, the set braces are required. Set braces tell a reader that it's that you're creating a set. So these are the integers that we need to understand. Now I want the integers between 2 and 5, and I want the integers between 2 and 5 inclusive. When I see the word inclusive, it means it includes the first and the last number mentioned. So this one wants me to list the integers between 2 and 5, and I need to include the 2 and the 5. So inclusive implies to include the first and last number. So I'm about to solve this example right now. So I'm going to give the set a name, and it's said to call it set A. So I'm going to write an A for the name of the set, and then an equal sign, and then I'm going to make set braces. If I don't have set braces that group the elements of the set, then it's technically not a set. So I'm going to put a set brace. I can't draw those so well. And then it looks more like the number 3. I really can't draw those that well. It's like, that's kind of a set brace. I don't really know that that's even better. Nevertheless, they look like that more so than what I'm drawing here. But this is my attempt at drawing that. So I wrote A for the set name, an equal sign because this is what set A equals to, and inside I'm going to place the integers between 2 and 5, and I'm going to include the 2 and the 5. And from my list up here, these are all the integers between 2 and 5, including the 2 and the 5. And those 4 numbers in this problem, these are considered the elements of set A or the members of set A. So we'd say 2 is a member of set A, or 3 is an element of set A. All right, so that's that example. A lot of what I write after this I've probably already said. In this little paragraph here, it says, let A be the set of integers between 2 and 5 inclusive, lists the elements of set A. A needs to be a set for this question to make sense, lists the elements of set A, and really it's really easy to become a set. Any words, numbers, or letters that you put inside of a set brace would be considered a set. So this would be considered a set B. So I could say the set B equals, I don't know, apple, orange, and grape. So in set B, it's the set of those 3 fruits. And again, to be a set, all you really need is the set braces. And then once we have the set braces, the objects inside the set braces are called members or elements. If I wrote something like this, C equals apple, orange, and grape, it looks like the exact same thing, except I don't have the set braces. All of a sudden now C wouldn't be considered a set because you don't have the set braces, and now these fruits they're not considered elements or members. So to become a set, you have to have set braces. If you don't have set braces and you still have a capital letter set and an equal sign, this is not a set. So B is a set, we'll say is considered a set, while C wouldn't be. So it's kind of ticky-tacky. All right, that's kind of everything on this first page. I think I've hit it well enough. So I'll move on, and even if I haven't said everything on this page that I've typed up, I've said enough that we can go forward and do the problems just fine. So each of the things here, I showed again what the integers were. And here when I describe the integers, I put more integers in my description. If you're going to try to establish a pattern, 3 is the minimum number. So if I had 3 numbers, if I just had written the numbers, how about -1, 0, 1, and did ... that would be probably the most primitive description that one would consider okay for a set that shows the integers. And maybe I should write I equals because it's a set, because it's in set braces, and I stands for integers. And sets are usually given capital letter names. This is a really weak effort at showing what the integers are, but if you have 3 consecutive numbers that are 1 apart, dots go to the right means to continue that pattern, meaning continue adding 1 forever to the right, and similarly 3 consecutive numbers reading from right to left, all 1 apart, getting smaller by 1 each time. The dot says continue going to the left forever, getting 1 smaller each time. Alright, so inclusive we talked about includes the first and the last numbers. And curly braces are the set braces. And if you don't show the set braces, then the object isn't a set. I didn't mention that the order of the element weren't important. When I wrote my set A, I wrote A has the elements 2, 3, 4, and 5. It turns out that had I written A equal to 4, 2, 3, and 5, or A equal to 5, 4, 3, and 2, or A equal to 3, 2, 5, and 4, my answer would have been still correct. The instructions just said list the elements of set A and place the elements in set braces. There isn't any requirement of ordering. So when I listed the elements of set A, it felt right to list them from smallest to largest, but it wouldn't have been wrong to list them in another order. But I mean, given the choice, even though all 4 orders are correct, given the choice, it's probably easiest to write if there's numbers that make up the elements of a set, just to write them in ascending order. But it wouldn't be wrong. All these are considered equal to set A. They're all set A, written just slightly differently. All right, so had the example that I'd given on the first page of notes used the word exclusive instead of inclusive, then I wouldn't include the 2 and the 5. And so for exclusive, we do not include the highest and the lowest number, which is going to be the first and the last number mentioned. So, same essential problem that we just did, the same example, but written with the word exclusive as opposed to inclusive. So, I'll do this example real quickly here. So, let A be the set of integers between 2 and 5, and then we tag on the word exclusive, which means I don't include the 2 and the 5. List the elements of set A and place the elements in set braces. And I've done that already. So, I know that I'm worried about integers between 2 and 5 for set A, and the integers between 2 and 5 inclusive are the numbers 2, 3, 4, and 5. Because it doesn't say inclusive, I'm deleting the 2 from the list, I'm deleting the 5 from the list, and then I'm writing the set A with an equal sign, putting the numbers inside the set braces, otherwise the A isn't a set, and then just putting the numbers that fit the definition of the set. And the definition excludes the numbers 2 and 5 and only includes 3 and 4. One more problem, then we get to the first group of homework problems. I kind of lecture up to the point where we can do some problems, and then I do all the even problems, and then we get into, won't be done with the section, we'll have more theory. But I don't want to build up too much theory without doing problems. So a lot of this section will be, I'll lecture some theory, do some problems, lecture some more theory, do some problems, and then eventually the section ends. So the next example, let B be the set of solutions to the problem x plus 5 equals 8. List the elements of set B and place the elements in set braces. So ultimately, my answer to this is going to be to write a set called B. So I'm going to write the letter B because that's the name of the set, an equal sign, and then I'm going to write set braces because we need set braces in order for B to be considered a set.
but in order to figure out the elements of set B, I need to take the problem that's in the definition of set B and solve it. So I just took the equation x plus 5 equal to 8, subtracted 5 from both sides, and I got x equal to 3. So B consists of all the solutions to that statement, and the only solution to that statement is 3, because if you plug in 3 for x, you get 3 plus 5 equals 8, or 8 equals to 8. There aren't any other numbers that are solutions to that set, so B only has one element in it, and B is the set that contains the element 3. And so this will be the nicest way to write that answer. Now I think we're ready for some homework problems. And throughout the semester, as I'm doing the homework, if I can fit both an even and an odd problem on the same sheet, I did it. Sometimes the problems were too long when they're big print to get both the even and the odd problem on the same sheet. But when I can, I do it. And my hopes would be either you'd watch me do the even problem on the sheet and then you would pause the video and do the odd problem, or you would not even need to watch me do the even problem. You'd pause the video, you'd do the odd problem, you'd check your answer, then you'd fast forward to the next problem. And the same thing. If you right now can do problems 1, 3, 5, and 7 without me doing 2, 4, 6, and 8, then do that. Just try to do problems 1, 3, 5, and 7 and fast forward to the next group of problems. If you have no idea how to do problem 1, then I will do problem 2, and that should inspire you to do problem 1. So I'll do problem 2, 4, 6, and 8, and see where we go from there. You should do 1, 3, 5, and 7 now. So problem 2 says set A is a set of odd numbers between 1 and 10, and I'm supposed to list the elements in set A and write my answer in set braces. So when I go to write my answer for problem 2, I'm going to write A equals, and I'm going to have a set brace, and then inside the set brace I'm going to put the elements of set A. Well, it doesn't say anywhere in this problem that my set A is only containing integers, but that's implied. When we have odd numbers, that's implying that we're not having decimals or fractions. To be an odd number, you have to be an integer. So if I just looked at the numbers between 1 and 10, that can be even or odd. That would be the integers between 1 and 10, because decimals and fraction aren't going to be considered even or odd. And then from this list of numbers that could be potentially odd between 1 and 10, I need to remove the even ones because I'm only allowed to consider odd numbers for my sets. So I'm going to remove the 2, remove the 4, remove the 6, remove the 8, remove the 10. So those are the odd numbers between 1 and 10. But anytime I'm listing a set, I have to determine whether I can include or exclude the first and the last number. Because of the word inclusive, I'm supposed to include the first and the last number mentioned if they're part of the set. So I'm supposed to include the 1 and the 10 if 1 and 10 fit the set definition. Well, 1 fits the set definition because it's an odd number, so I'm going to include it in my answer. But 10, because it's not an odd number, even though it's mentioned as an endpoint, I'm not going to put it in my answer because even though it's an endpoint, it's not an odd number too. So to be inside my set, I have to be between 1 and 10 inclusive, which means I'm allowed to include the 1 and the 10 if they fit the set definition, but it also has to be odd. So my set A is just going to have the numbers 1, 3, 5, 7, and 9. All right, so that should inspire you to do problem 1. So you can pause the video and do problem 1 and check your answer. For question 4, I'll do the same thing. Problem almost looks the same because I'm supposed to write the set of odd numbers between 1 and 10, and now it's exclusive. So I'm not going to include the 1 nor the 10. So to do number 4, I'm going to write B equals, and I have to have the set braces, otherwise what I've written isn't a set. And then I'm going to write all the odd numbers between 1 and 10. I don't need to write the evens and cross them out. I know they don't belong. And then in this problem, if the 1 and the 10 were odd numbers, they'd need to be excluded. The 10's already excluded because it's not an odd number, so there's no chance of it getting into my answer. But the 1 had a chance, and the word exclusive removes the 1 from my list. So my set B will have the numbers 3, 5, 7, and 9 inside set braces. I mean, it'd be nice if the set braces weren't so big, but I wanted to make sure I had enough room to write everything. So probably it would have been nicer if I said B equals the set 3, 5, 7, and 9. All right, so that should inspire you well enough to do number 3, and then I'll move on and do number 6. So number 6, set A is the set of solutions to the problem x minus 4 equal to 9. So I have to solve that problem, find the elements of set A, and then I can write A equals and then something in set braces. So I'm going to go ahead and figure out the elements of set A by solving the equation x minus 4 equal to 9. I do that by adding 4 to both sides. And the only element in set A is the number 13. So for my answer to number 6, I'm going to write the letter A because the set is called set A. I'm going to write an equal sign and then set braces. And then inside the set braces, I'm going to put the number 13. And that's the only answer that would be correct for this problem. And then one more of these problems. So we both have set B's. You're supposed to know what Neapolitan ice cream is. If it isn't, hopefully you have a phone or you can quickly figure that out. On a test, I wouldn't ask any question that involves knowledge that you might have to get off the internet that you might just not generally have. But I'm assuming most of you can do that. For my set B, in number 8, it's the set of days of the week. I'm going to write a B equals, and I need my set braces. And then the order's not going to matter, but I need to write the 7 days of the week. So it's going to be Sunday, Monday, Tuesday, Wednesday, all the way to Saturday. And I'm going to quickly run out of room. So I'm going to start abbreviating, and I'm completely okay with you abbreviating a problem like this. Because if I didn't, especially because I'm writing big for you to read it, it wouldn't have fit. So that seems like a reasonable answer. And then your set is going to have the 3 flavors of Neapolitan ice cream. All right, so that's the first group of problems, but we're not done with the section. The next group of problems will follow up a few pages of lecture. So the next concept that we need for sets is well-defined. And well-defined, a well-defined set is one that any informed objective person can decide if a given element is in a set or not. Again, that's probably a weak definition, and we'll do some examples to help you understand what that definition for well-defined. So well-defined, a set is well-defined if any informed objective person can decide if a given element is in the set or not. And again, so that's not a great definition, but if inside the definition of a set you see the word good, bad, or nice, that's probably that set's not well-defined. So I'll have 2 or 3 examples before we get to some homework problems. The first example says, is this set well-defined? So let M be the set of months with more than 30 days. Is this set well-defined? My answer is either going to be yes, the set is well-defined, or no, the set isn't well-defined. It's well-defined if any objective person that has the proper information can decide if you give me an element, is it in the set or not. So like for instance, if I said, March, well, does March have more than 30 days? If I didn't know whether it had more than 30 days or not, I can look at a calendar, become that well-informed objective person, and March does have 31 days, so it would belong in that month. So for each of the months, I can look at a calendar if I don't know the number of days in the month and determine if that day belongs in the set or not. So this is actually a well-defined set because there's no ambiguity as to whether a month belongs to the set or not. So this set's only going to contain months, and it's only going to be the months that have more than 30 days. More than 30 days means it has 31 days for months. So January, March, May, July, August, October, and December would be the months. I don't need to list the elements of the months. I just have to know whether this is a well-defined test set or not, meaning whether there's no debate or is there debate as to what elements belong in the set. So my answer, I could have just said yes, or I could say the set well-defined, the set is well-defined. It would have been okay if I just said yes. So the next example I have, let's see, be the set of good cell phones, and that word good probably makes this not well-defined, because if you asked me, if an iPhone is good, I'd say it's a good phone because that's what I have. I have an iPhone 5, somebody that has an iPhone 6 or whatever comes out after the iPhone 6 might say my phone is junk because its camera isn't that good. Or somebody that prefers Samsungs might say my iPhone's not a good phone, because that's a matter of opinion, whether a phone is good or not. So if I tell you a phone, like my mother's flip phone, she thinks it's good because it works for her, but for me, that probably I wouldn't consider that a good phone. So because whether a phone is considered good or not probably depends on the person that you're asking, that's not a well-defined set. There isn't a list of good phones versus bad phones that is universally accepted. So we'd say this set is not well defined, and again, it probably would have been nicer if I would have just said no, meaning is the set well defined? No. Or is the set well defined? Yes. Alright, so now we get a set of homework problems, and I usually match my problems up a little bit better than I did these, in terms of usually the even and the odd problems have exactly the same idea, and these kind of don't, but I think you can get by. So I'm going to do number 10, and you're supposed to do number 9. So when I look at number 10, I'm going to read the instructions first. Which of the following sets are well defined? That should probably be a question mark there. Write yes for your answer if the set is well defined. Write no if it's not well defined, just because I didn't want to have to write so much. So for 10, B is a set of GCC students whose GPA is 3.0 or greater. I think this is well defined, because if you point a student out to me and I can find their name and their student ID number, I can go over to the C building and get somebody there to pull up their GPA, and I can look at their GPA. If it's 3.0 or higher, I'd put them in the set. If their GPA is less than 3.0, then they wouldn't be in the set. So for B, for number 10, I'm going to say yes. This is well defined because there's a clear definition that's easy to decide whether someone is or isn't in the set B that's described. For your problem, goofy is kind of a word like nice or good. It's subjective, and whether somebody considers a dog goofy or not, that might differ depending on how you know the dog even. So this is probably not well defined, and so the instructions say write no if it's not well defined. All right, so for 11 and 12, I'll let you figure out 11. If you can't figure it out, then you can ask me it, and I'll do 12. And for 12, good, again, that's too subjective of a term. I might consider a student good that doesn't even consider themselves good. So to try to make a universal group of all good GCC students, there's definitely going to be debate within the ranks of who belongs in the set and who doesn't belong in the set. (13) and 14. I think I know the Great Lakes. If you give me a lake, I can at least tell you in problem 14 whether it belongs in the set or not. As it goes, what is it? Michigan, Huron, Superior, Erie, and Ontario, I think, are the Great Lakes. And so I would say yes, this is well defined, because if you give me a lake like Mead, you might think it's a Great Lake, but it's not one of the quote-unquote Great Lakes. And then your problem 13, I think that's probably a yes as well, because you can just go to, Wikipedia and figure out which years the Cardinals did win their division and which years they didn't. So it probably is a yes. All right. 16 feels a lot like the example that I did. I think the example I said good cell phones. Now I'm saying good smartphones. Nevertheless, the word good in a set description probably makes it not well defined. Similarly, nice is subjective. I think Phoenix has a nice climate. My dad thinks it has a horrible climate. So if there isn't a clear consensus that everyone, or most everyone, I think everyone would agree on, then a set isn't well defined. All right, so I'm sensing we're maybe halfway through this section. Maybe not quite halfway through this section. Oh, no, definitely not halfway through this section. Maybe a third of the way through the section. So next concept, so I want to lecture on some theory a little bit, and then we will do some problems. The next concept is finite versus infinite set. And then a finite set, it's possible, if you give me enough time, to write down every element. You may not want to write down every element because there might be too many elements. And then to be infinite, it's impossible to write down all the elements. This means infinite is just the opposite of finite. So if I gave this set, if I asked you if this set is infinite or finite, is it possible to write down all the elements? Well, these 3 dots means the pattern continues, but the pattern continues and it stops at 20. So A consists of the integers 1 through 20. And it only has 20 elements in it. So I can write down every element of A, so A is a finite set. So the instructions were, or the problem said, is A infinite or finite? A is finite because it is possible to write down every element of A, and that's what it takes to be finite. If it's possible to write down every element, even if it's a really large number of elements, it makes the set finite. Whereas the set B on this page, where it has the ellipses, the dots, that means the pattern goes on forever. I should have probably said that. Those 3 ellipses are, those 3 periods are called ellipses. That mean the pattern continues. And in this next problem, the set B, it goes on, but it doesn't stop. So it would be impossible. I can continue to write integers forever, but I'll never reach the end because the dot doesn't get terminated by a number. So B is going to be considered an infinite set because no matter how much I write, the dots tell me to keep going. And because the dots didn't have a number after them, I'm not going to stop. I'm going to go forever. That makes an infinite set. The next 2 problems have one problem has the word factors, one has the word multiples. Multiples and factors are words that you might have heard but not remember. So determine whether the set is infinite or finite. The set A contains the factors of 10. To be a factor of 10, you divide evenly into 10. You might debate whether you want both positive and negative factors. I probably could include negative numbers as factors. But the factors of 10 are positive 1, positive 2, positive 5, positive 10, and then if you want, negative 1, negative 2, negative 5, and negative 10, because each one of those numbers divides into 10 evenly without a remainder. That's what it means to be a factor. And so I'm able to write down all the factors of 10. There's only 8 of them if you considered positive and negative factors, 4 if you're only considering positive factors. So it's possible to write down all the elements of A, so A is a finite set. The next example has the word multiples. Multiples and factors are not the same. So determine whether the set is infinite or finite, and we have the set of multiples of 4. To be a multiple of 4, it's just 4 times any integer is a multiple of 4. And here are the positive multiples of 4. 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12. So 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44. It goes on forever. because the set of integers go on forever, and multiples of 4 is 4 times, any multiple of 4 is 4 times an integer, that list is going to be infinite. It's impossible to list all the multiples of 4. It's going to go on forever without terminating. So multiples usually give me an infinite list, or an infinite set, whereas factors are generally finite. In some of the problems that are coming up, I add some words to the problem that make problems that have multiples finite sets, and we'll get to that in a second. So you have to read. If you see the word factor, I think you can always think finite, but if you see the word multiple, it might add more to the problem to make that not the case, that it's infinite. So now some homework problems. I don't have to write down the factors, but I can. So if I was doing problem 18, determine whether each set is infinite or finite, the factors of 24. Well, 1 divides evenly into 24, 2 divides evenly into 24, 3 does, 4 does, 5 doesn't divide evenly into 24, 6 does, 7 doesn't, 8 does, 9 doesn't go into 24, 10, 11 doesn't go into 24, 12 goes into 24, and 24 goes into 24. And then if I wanted to include the negatives of each one of these, -1, -2, -3, all the way on to -24, those are all the factors of 24, and that's only, a dozen or so numbers. So this is considered a finite set. So if I'm asking for factors, that's always going to be a finite set. For 19 and 20, we're both asked to look at multiples. For my set, the multiples of 5, 5 times 1 is 5. Actually, 5 times 0 is 0. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. 5 times 5 is 25. And that's going to go on forever. I'm never going to exhaust the list of multiples of 5. Just multiply by the next integer, get another multiple of 5. So 20 is going to be an infinite set. These are the problems that have the word multiples that aren't definitely infinite. So when I look at problem 22, it talks about the multiples of 4, but it doesn't talk about every multiple of 4. It only wants the ones greater than 10 and less than 50. So if I looked at the multiples of 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60, they go on forever. But in this problem, I'm only considering the multiples of 4 that are greater than 10, so I'm not including those or any negative multiples of 4, and less than 50, so I'm not including those or anything bigger than those. These are the only multiples of 4 that are allowed to be considered in problem 22, because I'm not including any ones that are less than 10, that are less than 10. Actually, I'm not including anything less than or equal to 10, and I'm not including anything greater than 50. I'm only including the ones that are greater than 10, 12, and less than 50, 48, and anything between. So this is actually a finite set. Even though multiples inherently create infinite sets, if you're only looking at specific multiples, then you can have a finite set. For 23 and 24, if I'm looking for odd positive integers, I think 2 is positive, but it's not odd. 1, 3, 5, 7, 9, 11, 13. Those are all odd positive integers, and I can keep going. 15, 17, 19. It's never going to end because the integers don't end. I just put a ... And again, I don't, in my work, need to list the elements of the set. I just have to be able to conceive what elements make up the set, and then once I can conceptualize that list of elements, and then in my head I can know whether that's infinite or finite. And for 24, that's going to be an infinite list. All right. Oh, students sometimes do poor things with empty sets, or they use the number 0 like it's an empty set. An empty set is simply a set that doesn't contain any elements. And some people will use the word null set. I almost never ever say the null set. So an empty set is a set with no elements, and this is probably the nice way to write the empty set because you're using the nice set braces, and inside those set braces you write all the elements of set A, and there's no elements inside set A if A is an empty set. And so that's a nice way to describe an empty set. So this right here, when I see this, I call this an empty set because it has no elements. This 0 with a line through it also means empty set. So this also means a set with no lines in it. And that's probably somebody that was just lazy that didn't want to keep drawing the set braces. They just do that, and that would be an empty set. This is not an empty set because it has the number 0 in it. It's a set with the element 0. So an empty set, if using set braces, has nothing inside of it, and an empty set, if you're not using set braces, is a 0 with a line through it, and that would be an element that has a set that has no elements. And then here's a word description of an empty set. The set A is the months of the year where the average high temperature in Phoenix is less than 10 degrees Fahrenheit. That would be an example of an empty set because of the 12 months of the year, there isn't a month of the year that the average high temperature in Phoenix is less than 10 degrees. So that's an example. You can have empty sets. Here's some more notation. And this notation I talk about way too long right now because it doesn't come up in the homework, so I'm going to shorten what I say. Just because it's not so necessary. So this symbol, I read that as element. So that symbol means an element. That symbol means not an element. So if I made up a random set and I called it A, if A is a set that contains the numbers 1, 2, 3, 4, and 5, it would be correct to say 5 without the set braces is an element of A because 5 is in the listing of all the elements of A. So to see that symbol and for it to be used correctly, that means one of the elements inside set A will be the number 5. Similarly, this would be a true statement because this says 6 isn't an element of A, and for this particular set A, 6 isn't in the list. So for these symbols to be used correctly, to the left of the symbol we generally have an element which was not in set braces. If that element is inside the set, then we use the element symbol to use it correctly. 5 is an element of set A. And if that element's not inside the set, to use that element correctly, we'd say it isn't in the set, and this is saying it's not in the set. So 6 isn't in A, 5 is in A. Not so big of a deal. I'll use this element symbol every now and then, just because I'm used to using it, and that just need to know that means if I see that symbol, then that means 5 would be in the set A, and usually we don't write to the left of the set A set braces. Usually what's to the left of that element symbol is something that's not inside set braces because the elements generally aren't sets. I think that's all I want to say there. So I'm going to skip this whole junk right here. It doesn't come on the test, and I think it's more confusing than it's worth. I meant to delete it from this section, but I didn't. It's just kind of there. All right. Before we can do the next problems that are kind of homework-y problems, we have to know a couple of words. And the first word that we need to understand a definition for is the word natural numbers. And we'll use natural numbers a lot in this section and a lot in this chapter. So the set of natural numbers is usually given the letter capital N, and it contains positive integers that are, or integers that are greater than 0. So the set of natural numbers, again, we usually write it with an N. It has the numbers 1, 2, 3, 4, ... and it goes on forever. And again, to establish a pattern, you need at least 3 numbers. You could use 4 or 5 numbers if you want to. So natural numbers are integers that don't include the negatives and don't include the 0. So that's first definition that we have to know for the next group of problems. And then the second definition that we're going to need is cardinal number. And the cardinal number of a finite set, cardinal numbers don't apply to infinite sets, is the number of elements in the set. And symbolically, if the cardinal number for set A has a letter N in it, but it's a little n. So natural numbers are usually given a capital N. And if I see that symbol, a small n, and then a set name inside of parentheses, this is asking me to find the number of elements in set A. So the next example, the instructions say find the cardinal number of set A. I could have just written this, find n of A. So this sentence and that symbol asks me to do exactly the same thing, and what it asks me to do is find the number of elements in set A. So there's not really any algebra to do, it's just counting. If I look at this set A, it has 1, 2, 3, 4, 5, 6 elements in it. So it has 1, 2, 3, 4, 5, 6 elements in it. So the cardinal number of set A is 6. And it wouldn't have been wrong if the question said find the cardinal number of set A. If I said answer the cardinal number of set A is 6, this would be correct because it answers the question that was asked. But it's probably not the best answer because it's really wordy, and this version of the answer means the same thing because that symbol right there means the cardinal number of set A, and that's what I'm trying to find. So I'm going to use this symbol more so than using a sentence definition for the cardinal number, just because it's easier for me to write. But if you are asked to find the cardinal number and you write a little sentence, it's completely fine. All right, so another example before we get into some homework. Find the cardinal number of set A, or the number of elements in set A, where A is a set of natural numbers less than 8. Well, in order to answer the question how many elements are in set A, or what the cardinal number of set A is, I need to list all the elements of set A. And A is natural numbers. Again, natural numbers it's an infinite set. And that's a list of natural numbers that are going to help for this problem. So I need to list the elements of set A before I can find the cardinal number of set A. And in the definition of set A, it says less than. Less than means not equal to. So my set A is going to include only the natural numbers that are less than 8. It's definitely not going to include the 9, the 10, and the 11, or anything after 9, 10, and 11, because those numbers are bigger than 8. It's also not going to include the 8 because 8 isn't less than 8. If it said less than or equal to, I would include the 8. But it doesn't say less than or equal to, it just says less than, so I'm not including the 8. So the set A that's mentioned here only includes the numbers 1, 2, 3, 4, 5, 6, and 7. So now that I know the elements of set A, I can answer the question. Find the number of elements in set A. I just count the elements in set A. There are 1, 2, 3, 4, 5, 6, 7 elements in set A. So A has 7 elements, so the cardinal number of set A is 7. So n of A equal to 7. Again, for my answer, I could have written, it wouldn't be wrong. I can say the cardinal number of set A is 7. That would be also correct. If this was a test question and you only wrote 7 for an answer, I wouldn't take any points off. Because I usually am a pretty easy grader. So I'd give you credit for that. Quite honestly, it probably shows your lack of attention to detail, writing an answer like this as opposed to one of these. And in this class, there's almost no algebra. The algebra inside the class is really easy, like solving the problem, x plus 3 equal to 8 kind of algebra. So the algebra is not going to be hard in this class, but the detail, the definitions, and how to write answers is going to be important. And it's kind of almost predictive. Like if this was a test question and I looked at 3 different students' answers and one student answered this, another student answered this, and a third student answered this, I would bet you a lot of money that the student that answered this gets the lowest grade of the 3. It would almost just be shocking if they didn't, probably because they just blew through the material, didn't probably focus on it as much as somebody that did this, and it just kind of almost shows laziness. And being lazy in this class is probably going to sink you. It's you probably can pass the class, get a B or a C with being lazy, but to get an A in the class, you just kind of have to go through and do the work. It's not a hard class, so if you just do the work and suffer through these videos, you should be able to get an A without really killing yourself. I know these videos are just painfully boring. I'm sorry about that. You'd think I should work on making them more interesting, and making them more interesting, I don't really know how to do it other than making them longer and just babbling on about stuff that most of you don't want to hear. So they kind of is what it is. So sorry about that. Try to write in different colors to make it interesting, but I don't think that really does much for anybody. So 25 through 34, getting close to the end of the homework. We got to get up into the 40s. So there'll be one group of problem after this, I guess. So we're given the instructions, find the cardinal number of the following sets, that is, find the number of elements in each set. So in order to do this, I have to probably list the elements of the set. I don't really need them in set braces. So my answer for problem 26 is either going to be symbolically the cardinal number of B equals, or in words, the cardinal number of B equals This is actually my second time doing this video. I watched the first go around of this video and I wasn't that happy with it. Called myself an idiot like 4 times, and I think I do that a lot this semester in these videos, but I was like, I don't need to call myself an idiot on the first video, so you'll find that out, I guess, in time. So anyways, 26 says the set B is even natural numbers between 5 and 10. Well, if I looked at natural numbers and I looked at even natural numbers, these are the even natural numbers. Those are the even natural numbers, but I only want the ones between 5 and 10. So I'm not going to want the 2, I'm not going to want the 4, I'm not going to want the 12. I'm not going to want the 14 because those aren't between 5 and 10. And then I looked at the word inclusive, and inclusive means I'd include the 5 if it fit the set definition. I'll include the 10 if it fits the set definition. Well, 5 isn't even, so it doesn't belong in the set, but 10 is even, so it does belong in the set. So B is the set that contains the numbers 6, 8, and 10. So the cardinal number of set B is 3. So one of these two versions of the answer would be fine. And again, I will write that because it's more efficient for me. (28), and you can do 27. So I need the odd natural numbers greater than 2 and less than or equal to 5. So I'm going to list the odd natural numbers. Odd natural numbers are 1, 3, 5, 7, 9. And I don't need to include the 1 because it's not greater than 2. And I don't need to include the 7 and the 9 because they're not less than or equal to 5. So I'm going to try to focus on the ones that are both greater than 2 and less than or equal to 5. And so I didn't include the 1 because it's not greater than 2. I didn't include the 7 and 9 because they're not less than or equal to 5. But these two numbers, 3 is greater than 2, and it's less than or equal to 5, so it belongs in the set because it's an odd natural number as well. And 5 also is going to belong in the set because it's less than or equal to 5, so I'm going to include the 5. So the set A that's described in problem 28 contains the elements 3 and 5. So for my answer for problem 28, the nice way to write the answer is the number of elements in set A, or the cardinal number of A, is 2. Or, again, I can say the cardinal number of set A is 2. You could just write the number 2, but that's not the best answer. And there are definitely teachers on this campus that wouldn't give you credit. They take points off if you just wrote the number 2. All right, so 29 and 30, I'll do 30. The set of natural numbers less than or equal to 5. So if I start writing my natural numbers, they start at 1. They aren't smaller than 1. And then less than or equal to 5 means I don't include the 6, 7, and 8 or anything bigger than 5. I can't go less than 1 because natural numbers start at 1. And I'm supposed to include the 5 because it's less than or equal to 5. In your problem, you're going to make a list similar to this, but you're not going to include the 9. You're only going to include the 1 through 8. So my set A is the set that contains the numbers 1, 2, 3, 4, and 5. It includes the 5 because they are equal to. And for my answer, I could write it in words, but I don't like writing it in words because it takes too long. So I'm going to write the cardinal number of set A is 5. If you wrote a capital N, I hardly care. It's not, I can live with that. I don't think that's, although it's customary to write a small n for the cardinal number, I think the letter N would be sufficient, and I might at some point on the review write a capital N. I don't think I do, but I might have. Because capital N usually means natural numbers. So 31 and 32, we don't have to figure out the elements of the set. That's given to us, so these are way easier. So 32 says find the cardinal number of set B, where B has 1, 2, 3, 4, 5 elements. So the answer to problem 32, the cardinal number of set B is 5. There's no work at all to do when the set is given to me in such a nice, when all the elements are listed. I don't have to figure out what the elements are. For 34, find the number of elements in set D, where D contains 0. It's not the empty set, it's the set that contains 0. And that's 1 element. So the number of elements in set D is 1. And you can do this 33. So we're going to move on to our last set of problems, which is going to have 2 new words. that we have to understand what they mean in terms of sets. And they're not hard. There isn't anything in this chapter that's hard. It's just a lot of terminology that's going to bog you down. All right, so the first of the two words that we need to understand is equal, and that's a word that we're used to, at least, in outside of sets. And two sets are equal if they have exactly the same elements. So here's an example. Our sets A and B equal. Well, A have the elements A, B, C, D, and E, and B has the elements A, B, C, D, and E written in opposite orders or different orders. That doesn't keep them from being equal. If they have the same exact elements written in the same order in different orders, they're considered equal. So are these sets equal? Yes. So it's a yes, no question. Are they equal? Yes, they're equal, or no, they're not equal. For the next example, A has the elements 1, 2, and 3, and B has the elements A, B, and C. Those aren't equal because they don't have exactly the same elements. They have different elements. And then the last example, are these sets equal, where A has 1, 2, and 3, and B has 1, 2, 3, and 4. Those aren't equal as well because B has a 4 that A doesn't. So to be equal, you have to have exactly the same elements. Doesn't matter the order that the elements are written in. The last concept that we need is set equivalence. And to be equivalent, two sets are equivalent if they have the same number of elements. So this is a really nicely slick definition. Set A is equivalent to set B if they have the same cardinal number, and then I just wrote it in words. Two sets are equivalent if they have the same number of elements. So same example with the word equal changed to equivalent. Are these sets equivalent? To be equivalent, they need the same number of elements. The cardinal number of A is 5 because it has 5 elements. The cardinal number of B is 5 because it has 5 elements. Because they have both the same number of elements, these are considered equivalent. So these two sets, they were equal and they're equivalent. They're both. These sets, are these equivalent? Well, here, set A, the cardinal number is 3 because it has 3 elements. Set B, the cardinal number is 3 because it has 3 elements. And it is, yes, these are also equivalent. So they weren't equal because they had different elements, but they are equivalent. So the bar is lower to be equivalent. To be equivalent, you have the same number of elements. To be equal, you have to have exactly the same elements. And then this last example, the first set A has 3 elements. Are these equivalent? And it's going to be no, because the second set B has 4 elements. And two sets are only equivalent if they have the same number of elements. The elements can be the same, but they don't have to be the same. These sets aren't equivalent because A has 3 elements and B has 4 elements. To be equivalent, you have to have the same number of elements. So equal, you have to have exactly the same elements. Equivalent, just the same number of elements. The elements can be the same, but they don't have to be the same. So, a couple examples here. Determine whether the sets are equal, equivalent, or neither. So I look at these two sets, say, are they equal? Well, this has A, B, C, and D. That doesn't have A, B, C, and D. They're not equal because to be equal, they have to have exactly the same elements. This has elements that doesn't have. They don't have exactly the same elements, so they're not equal. But the cardinal number of A is 4, and the cardinal number of B is 4 because they have 4 elements. So these are equivalent sets because they both have the same number of elements, and that's what it takes to be equivalent. So they're equivalent, but they're not equal. So determine whether the sets A and B are equal, equivalent, or neither. They're only equivalent. They're not equal. And it wouldn't be right to say neither because they're one of the two. Next example, determine whether these sets A and B are equal, equivalent, or neither. And if I look at the sets, they both have A, they both have B, they both have C, they both have D. They both have the elements A, B, C, and D. That makes them equal because even though the elements are written in different order, they're equal. and they both have 4 elements because the number of elements in set A is 4 and the number of elements in set B is 4. That makes them equivalent. They're equal because they have exactly the same elements. They're equivalent because they both have 4 elements. So for these two sets, A and B, in this problem, they're both equal and equivalent. And then the last example before the last group of homework, determine if these sets are equal, equivalent, or neither. And if I look at these two sets, they're not equal because the set B has the element A and the set A doesn't have the element A, so they're not equal. And they're not equivalent because this has 3 elements and that has 4 elements. So they're not equal because they don't have exactly the same elements. They're not equivalent because they don't have the same number of elements. So my answer here is these are neither, because my choices were determine whether the sets are equal, equivalent, or neither, and these are neither. So last group of homework, determine whether the sets are equal, equivalent, or neither. These should be easy, hopefully. There's got to be something in there that makes them a little bit harder. So again, our 35 and 36 don't line up the same way because we'll have different answers. So first thing I want to look at to see is whether my sets are equal, and they're not equal in problem 36 because A has a 1 that B doesn't, so they're not equal. And then similarly, I look at the number of elements. A has 4 elements, B has 3 elements. That makes them not equivalent. They're not equal because they both don't have the number 1. They're not equivalent because they don't have the same number of elements. So my answer for problem 36, these are going to be neither equivalent nor equal. You're going to have both on yours. For 38, they both have A, they both have B. These are equal sets because they have exactly the same elements. Set A has 2 elements, set B has 2 elements. So they're also equivalent. So my answer for 38 is these are equal and equivalent sets. Our 39 and 40 are similar, even though they look different. For 40, they're not equal because A has the number 1 in it, B doesn't have the number 1 in it, so they're definitely not equal. But in terms of being equivalent, A has 3 elements, B has 3 elements. That makes these only equivalent. They're not equal, but they both have 3 elements, so they're equivalent. Again, we have different answers for 41 and 42, but that should be okay. These are definitely not equal because A has a 1 in it, B doesn't have a 1 in it, so they're not equal. So they're not equal, and they're not equivalent because A has 3 elements and B has 4 elements. So they're not equal, so I can't write equal. They're not equivalent because they don't have the same number of elements, so I'm going to write neither for my answer. And then just a few more problems. 44, 1's here, 1's there, 2's here, 2's there, 3, 3, 4, 4, 5, 5. They have exactly the same elements written in a different order. That's okay, they're still equal. A has 5 elements, B has 5 elements. They're also equivalent. So my answer for 44 is they're both equal and equivalent. And then you can do 43. And then when you're done with 43, you have a problem 45, but I don't have a problem 46. So you need to finish up by doing problem 45 as well. And so hopefully you got through the video, stayed awake through it, and you were able to do all the odd problems. And if you've done all the odd problems, then you're done with this section. And that's kind of my goal, is probably every time you watch a video that you just sit down long enough and you just do it and you're done with it in however the hour or so that it takes you to do the section. Alright, so I'm going to shut down the video. If there's something you didn't quite understand, then come visit me and I will explain it to you the best I can.